can be done.
Yeah.
It'll be all right. Well, if he does,
Purdue?
Yep.
if you do
I'm
activity
Derek. Nice to
coefficients,
meet you.
Nice to meet you, Derek.
the data table.
I didn't know I was being filmed. Added stress.
Yeah, because you have to like graph it. I mean, I would think you could give us like the plot sheets. Otherwise, having a graphing calculator for that would be basically required.
Yeah, because otherwise you can't. Because you can't extrapolate the data. It doesn't work from the two endpoints because
Yeah.
it's the average 12 points online. So yeah, you basically have to have a computer graphing.
Yeah.
I'm not terribly worried about it just because the entire report took up like half a page in my notes. And so it's like basically all the equations that we have and
Yeah. I think you'll go fine. I hope it will at least. I can devote as much time as I'd like to because I can exam on Monday. Got a writing for the profession paper to like I have to have it done by tomorrow. And then I have an interview. And like
Alright, Carolyn, this is Derek. I forgot again.
So like
I'll be there in the
I'm
morning.
busy early this week, so if we could do it like
I'll just take my truck home, that way I can't.
That's
Oh my God, I'll take my truck home. I'll just take my truck home tonight with the lift gate on it, that way I'll be able to
It's
say,
easy for
oh, I
internships,
can't
that's what he's saying now.
So I can't forget. Alright.
but
Oh, what about 8 o'clock? Yeah, I'll be about 8, yeah, somewhere out in there. You're just right across the street, I live over on Hattie. Yeah, crazy, eh? Oh, I just work in Tulsa, and I've been working on a big project, I just, you know, I guess forget.
have to start on this project.
Alright, we'll get it.
Yeah. I mean, the writing professional thing I am doing, I
John,
trust.
you're gonna get me a little punished for that.
Because that I can get good sources for this project.
I guess I could. We're working. We should be
Yeah.
on our final writing compositions thing. It's like our big informational research paper. It's 20 pages.
20
That
pages?
includes a lot of other stuff. The paper itself is like 7.5 pages.
Okay.
It's like 20 pages worth of stuff, but the actual content is much shorter. And then it'll, but I'm not doing any plasma analysis. Yeah, I've sort of done a little research. It's one of those things, like it's writing, and it's a big project, so I'm definitely gonna put it off till way too late and then just do it for the last time.
Yeah. It's one of those things where like, just marathon.
Yeah. It's gonna hurt.
Hurt, but.
They're hurting that way.
Yeah, marathon minimizes the pain by localizing it so one.
It actually minimizes it, but at least localizes it.
Yes.
Better for me,
I
yeah.
think it does minimize it because if you don't marathon it, then you're stressing about whether it's good enough for a long
I'm not
time.
positive. This is what I would assume.
Whereas I only stress for a
And
little
they said that I
bit.
did very good job of answering questions. So that's like,
I know
I would just like continue to do
it's
that.
not gonna be graded that
If you don't
harshly,
completely know
like I saw,
something,
like at least a decent job on it.
Yeah.
It's enough content that won't take any time to actually.
Yeah, me
One of the things that I started doing over the weekend.
I can like pre-write.
My interview with a food company.
And plus you're
I'm doing food stuff, so I have a food engineering textbook. I've been reading through it for a little while.
Yeah, my
Kind of
memos do,
started
because
reading it last weekend. Really interesting stuff. Especially
Yeah,
when it's
that's
like,
what they knew, you know,
yes,
like.
here's how you can find
It kind of sucks for everybody else.
conduction coefficient for like food with this much moisture, protein and fat. One of the things that it said was ash, and I'm like, how much ash is in my food?
Mac and cheese is 0.2% ash.
It was a bigger percentage than that.
Yeah,
It was like 5% ash, and I was like, how much ash is in my food? And then I had like specific heat capacity of green beef with 73% fat, or 73%.
So that's good. Poland at like 15 atmospheres and 200 degrees Celsius. Pretty
Yeah, that's correct.
It's I'm reading how to it's we can do scientific answers to common real world problems. And it's like we keep saying, the thing I love about physics and math is that you can plug numbers into the equations and physics has to give you an answer. It's like, it doesn't matter if I'm asking a ridiculous question, like what is the fuel efficiency of my house on the highway? It still has to give me an answer. Physics doesn't care if your questions are ridiculous.
She did.
This is the wrong folder.
Yes, but,
My interview's at 3, so I'm not going to start. My passport is over here. I need to take that out of here.
I have to give you a passport.
Are you going anywhere fancy? Or
No,
just
I just
fire?
need the
I'm so freaky to finish that paper.
The doctor got me.
Interview. And everything else.
She, for the conference, she asked me.
Got nothing next week?
I wonder if they actually made it easier this time for you to keep on
I think you did.
because like the first problem last time, it couldn't have gotten any easier as far
Yeah.
as people have numbers. You just got numbers and
Just know how you calculated the change.
It was
I
weird
wonder
how
if
we
they're
got,
all gonna be more like that.
we got like a Poisson distribution. No, it was a binomial distribution. Like
Yes, it was like,
not here, but here.
that is wrong. Like, this was wrong.
That is the hardest thing to like curve for.
It's like, 'cause I can't just shift this because that doesn't make any sense. It's like half the cost of math at 120%.
Yeah,
Yes, but I don't.
I'm definitely gonna use the extra credit. The HISIS thing.
At least look at it. Get a little familiar with it.
Well, the kid also that he was like, I
When's that?
appreciate
Is that a time beginning of next
I was
week?
like, oh.
Yeah, starting next week.
I didn't go that far. Give an equation to the
No, I think it's by Friday.
You just been doing the example problems? I haven't even started.
AICD just was like the slides.
No, and I was like, we've never had to understand. Yeah, we just use it.
I don't get partial problems at all.
You see, the thing about that is Wednesday is actually
Well,
before Thursday.
I don't think it's hard, we did not teach that well at all.
You'll be back.
Did you try to do that?
I knew that's the funniest thing there or something.
I really should.
I'm confused as to what the problem was.
I thought I was gonna be able to wake up early and start different reasons.
You're both saying the same thing.
I was not confused. You were confused.
All right, it looks like it's about 12:30, so let's get this show on the road. Guess I'll pass out the sign-in sheet so you guys can let us all know who's here. My name is Ben Pernew. I'm talking to you guys today about biogas flares and biogas systems. I have worked at John Zink for close to 3 years now as a biogas applications engineer. So designing and selling these things is my day job. I'm a TU grad twice over. Had to come back because non-applied sciences don't pay the bills that well. So kudos to you guys that did engineering the first time through. All right, so here are our objectives for the week. First, we're going to explain what biogas is, where it comes from. There are some rules and regulations that dictate how we have to handle our biogas, what we can do with it. Then we're going to go into biogas flare design, biogas flare components. There are two kinds of biogas flares that we're going to get into, open and enclosed units. There's also a couple of specialty pieces of equipment that we will very briefly touch on. And lastly, beneficial use. We have all this biogas, so we should do something with it, and we'll talk about that on Thursday. And if anybody has any questions at any time, just shout it out, raise your hand, whatever. Try to keep it pretty relaxed. All right, so biogas is gas mainly of a biological origin, strangely enough. It has two main constituents that we're going to be dealing with, methane and carbon dioxide, just depending on what the metabolism of the bacteria that made the gas is producing as its waste product. We've got pictures here of most of our main sources of biogas in the world, livestock and farming. We've got a landfill right here, a wastewater treatment plant down in the bottom corner there, and beer and liquor fermentation will release a lot of biogas as well. So these are what we're talking about when we talk about biogas. But of all these sources, the majority comes from landfills. About 60% globally originates in landfills. The day they hired me, they asked what I knew about landfill flares, and I said, what is a landfill flare? Why do you have a flare at the city dump? And it turns out that we're producing just vast amounts of flammable gas as your garbage decomposes over years and years and decades and decades. After a landfill is closed, we'll cover it up and it will keep producing gas for about 30 years. So you can find landfill flares in some pretty strange spots, and that's what we see in this slide here. This is a golf course built on a closed site landfill. Here's your enclosed flare. This right here in the bottom corner, that's a Home Depot. We have a landfill flare in a Home Depot parking lot up in the Northeast. You can't see the flare in this picture, but this is another closed site landfill. They just built it up so high that it is basically a mountain now. So they're everywhere. You might not even realize when you're looking at a landfill. They do a pretty good job of disguising these things these days. We got to get into the anatomy of landfills a little bit. How are we collecting this gas? How do we make sure we're not just venting it into the atmosphere? Over here, whoa, what's going on? Okay, so over here are a couple pictures of just kind of the start of landfills. They'll dig a big hole and put usually like thick plastic sheeting at the bottom of it, because in addition to your gas, you're making a lot of liquids from that trash decomposition, as well as rainfall, snow. All this stuff is just going to collect in your open landfill pit, and you don't want it leaching into the ground. That would be an environmental catastrophe. We have a lot of Superfund sites in this country that are really old landfills that didn't do any of this containment stuff, and so they're leaching like chlorinated hydrocarbons and ammonia and all sorts of horrible things into local drinking water. We don't do that anymore. Now we collect it. So this is kind of an idealized drawing of a landfill. You can see that the different layers of trash are separated into these things we call cells. So you have the plastic sheet at the bottom, then we pile up a bunch of trash, and then we cover that with more plastic sheeting, pile up a bunch of trash, and we keep doing that until we have that mountain that you saw on the last slide, and then we close up the landfill. Now, we have those two waste products in the landfill, the waste of our waste. This orange path right here is our liquids collection. Landfills will generate thousands of gallons a day of what we call leachate. This is the worst water imaginable. It's water that's been percolating through the landfill for years. It's like Satan's coffee pot, basically. And so we will put pumps in landfills, and we send that all off to a collection site. Usually that's just an on-site pond, but they can also truck it off to wastewater treatment. And there's a couple other weird things that some sites do with it. You can actually kind of shoot it straight up into the air using a fountain. And if you're in a dry, hot enough climate, it'll evaporate that way. But usually we're trucking it to a wastewater plant, or it's sitting in a pond. These blue lines here are our gas collection system. After we've sealed up a cell and we give it some time to start generating that gas, they actually send out field service teams to basically start drilling. They drill holes in the landfill. They can go down up to about 200 feet with our modern landfill drilling technology. Once you have these vertical wells, you put in a pipe, perforated HDPE usually, and up here you'll have a centralized gas header with blowers hooked onto it, and those will apply suction to your gas collection system in your landfill. So you want to keep steady, constant pressure on that landfill gas collection system, and either you're doing a beneficial use of it, which we'll get into on Thursday, or you are flaring it, and that is where I come in. So here's what we talk about when we are talking about landfill gas. It's usually an even 50-50 split between methane and carbon dioxide, but depending on the richness of the organic matter in your waste, you can have methane a little higher, a little lower if you have like a lot of electronics and other things that don't want to degrade in your waste. Nitrogen, oxygen, there's generally not going to be much of that in there because the bacteria will very quickly exhaust any oxygen in your landfill. The aerobic digestion dominates in the early stages of a landfill, and then once we exhaust that oxygen supply, that anaerobic digestion kicks in and we start making lots and lots of methane. So there's also just assorted other waste products in there, ammonia, hydrogen sulfide. You can find heavier hydrocarbons, just some real terrible stuff. We've come a long way. This is what landfill flares used to look like. You just got a pile of rocks, and you would send a guy out with a lighter, and he would stick it over the open vent and run away, hopefully fast enough. We do a little bit better of this now, and so hopefully I can demonstrate just how far we've come before the end of the day. Is that me?
Yeah, blue speaker, just unplug the cable behind it.
Okay. Much better. Oh boy. Okay. So landfills are subject to EPA regulation. Like a lot of other major emitters, they are subject to something called the New Source Performance Standards. Basically, if you hit a certain threshold on like pounds per year, tons per year of certain pollutants, you have to install a cleanup system, a collection system, something like that. Not just for the methane, but also odorous compounds in the case of landfills. You'd be surprised how many landfills are like in really nice neighborhoods, and the neighbors generally don't want the smelly landfill gas leaking into their homes. So the EPA thought it was worthwhile to make sure landfills couldn't just vent free landfill gas into people's homes. So for sites that don't have enough emissions to require NSPS gas collection, they can still install these systems and get tax credits through Kyoto Protocol. This doesn't happen too much in the United States because we don't really care about the environment in the United States, but in a lot of South American and Asian countries, you'll find a lot of sites that very rigorously monitor both their gas production and their emissions and the destruction efficiency in their flare so that they can get money for the pollution reduction. I'm sure this is all old hat to you guys at this point, but we're just gonna very briefly go over what combustion is before we get into biogas anymore. Basically, we're talking about the complete oxidation of hydrocarbon species, releasing heat, releasing water, releasing carbon dioxide as a byproduct. Methane is one of the more difficult hydrocarbons to combust. It has a pretty high autoignition temperature. We want to maintain a flame up above that 999 degree Fahrenheit threshold so that our new landfill gas that we're pulling into the flare is combusted by the old landfill gas that came into the flare. We want a self-sustaining combustion reaction, and so we have to keep it over this, this temperature. We also know just how much heat is going to be released when you burn a set amount of a particular hydrocarbon. Methane will release 909 BTUs per standard cubic foot. So it's there's less heat coming off methane than there is from most other hydrocarbons. You've probably heard about guys that would like replace the propane tank on their barbecue grill with a natural gas line, and all of a sudden they can't cook their burgers anymore. That's because they are getting about 1/3 the heat from the same amount of gas flow that they were with the propane. Here's our idealized biogas combustion reaction. It's not going to look like this in reality. There's going to be so much extra stuff in there. But basically we have methane and 2 moles of oxygen with a bunch of bystander nitrogen. Again, it's just idealized. It's not always a bystander nitrogen. And we'll produce carbon dioxide and heat and water with most of that nitrogen coming out as a product as well. The flammability limits of the hydrocarbons are pretty important. We want to make sure that our fuel is finding enough air to actually sustain that reaction. We can have problems, not only the ending of the combustion reaction, but some elevated emissions and less good destruction efficiency if the fuel can't find the air and the air can't find the fuel. So with our biogas, we want to make sure that in a control volume of gas, we have between 5 and 15% of that volume is methane. If you drop below 5%, suddenly your air isn't finding the fuel and the combustion will stop. And if you go above 15%, suddenly your fuel isn't finding oxygen and it's going to shut off that way. So you want to we try to tightly control the amount of air that's getting to the flame, so that we are staying in the happy combustion zone. And this is just kind of a visual representation of what that looks like. You need a lot of air for just a little bit of methane. And it gets even more and more drastic as your hydrocarbon chains increase, and each one of those carbons needs so much oxygen to oxidize, and it gets pretty wild, pretty skewed over to the 95% oxygen as a starting point. This is more what it's going to look like. You're going to have excess oxygen, and we want excess oxygen. You can't guarantee perfect stoichiometric mixing of your fuel and your oxygen in your flare. So you want to make sure that you have plenty of excess air, usually 50 to 75% excess as a starting point. But again, we want to stay below that upper flammability limit so that we are keeping combustion going. That excess air in some flares, it's not just for maintaining combustion, but that's also how we control temperature. We'll get into enclosed flares, which are our type that does control the temperature of the reaction to kind of maintain the parameters that we want. So, like I said, we've talked about idealized combustion reactions so far. And that's what we have here. We want carbon dioxide, we want water coming off. Unfortunately, there's going to be a whole bunch of other stuff that comes with it. You're going to get carbon monoxide, you're going to get nitrogen oxides, what we call NOx, as well as unburnt organic compounds, and then sulfur oxides, or SOx. And we'll get into how these are all made, what we can do to prevent them from being made, and why we don't want them to be made. So first up is the volatile organic compounds. These are generally, it's an interchangeable term with non-methane organic compounds in the landfill and biogas industry. It's any hydrocarbon that's not methane, usually not ethane, but benzene. Any of your like chlorinated hydrocarbons will be pretty common in landfill gas, and you need to guarantee as a minimum 98% destruction efficiency for all of your non-methane organic compounds in your flare per EPA standards. You can be subject to heavy fines if you are not achieving that. And this is the destruction efficiency that I'm talking about. This is taken on a mass basis. So let's say we have 100 pounds of methane going in. We need to make sure that we only have 2 pounds coming out at most. We need to be burning off 98% of that, fully converting it to carbon dioxide. So yeah, there we go. Both open and enclosed flares need to guarantee 98% destruction efficiency, and in some jurisdictions it's higher than that now, and we'll talk about what we do in that case on Thursday. All right, so carbon monoxide and NOx. These are going to be our most common pollutants that we have in the flue gas from a biogas flare. And what causes them? So first off is going to be the fuel composition. This is really big, especially for NOx. As you get a richer gas, so like in the case of biogas, methane content is increasing. Let's say we're at a wastewater plant. Wastewater doesn't often have 50%. It will be north of 60, 65% methane in its gas. So we're going to have a much richer gas, much richer fuel, and as a result, our flame temperature is going to increase. And that hotter flame is going to generate more of the nitrogen oxides, which is basically you have nitrogen in the air, you have oxygen in the air. The heat of combustion will actually cause those two atoms to break their bonds and then fuse together. We don't like NOx. It's a cause of acid rain, smog. It has a pretty good heat trapping capability, so it's a potent greenhouse gas. Temperature, we just talked about the flame temperature, but also the stack temperature, the temperature that we're holding that enclosed flare at, that can have a lot to do with the amount of carbon monoxide and the amount of NOx we have coming out the top. If it's too hot, NOx. If it's too cool, suddenly we don't have very good combustion occurring, so it'll be incomplete combustion, and suddenly our carbon monoxide numbers are going up. So it's a real delicate balancing act, trying to find the right temperature to make sure you have reached the best compromise point between your NOx going up and your carbon monoxide going up. Oxygen. This is going to be especially big for carbon monoxide. Carbon monoxide is formed when you have an incomplete combustion reaction, so everything's not fully oxidized. If the fuel can't find enough oxygen, it's not going to form CO2, it's going to form CO. And so you want to have a good air supply. You want to ensure you have good mixing of your gas and your air. And we have a few different ways of making that happen that we'll get into when we're designing the flares. And then residence time. How long is the fuel, is each molecule spending at my combustion temperature? If I only have about half a second in the flare, I can't really guarantee that everything is going to be fully oxidized there. We want to keep it as a minimum at about 0.7 seconds. And generally we'll design for above a second because that will up the destruction efficiency even more. So this is the incomplete combustion that generates carbon monoxide. We're back. If you don't have sufficient oxygen, you're not going to have enough to make the full carbon dioxide reaction because it takes twice as much oxygen. So if the fuel wants to oxidize, it wants to oxidize all the way to carbon dioxide, but if it can't, it's happy to settle for carbon monoxide, which, can kill you. So we don't like to make it. We want to keep that low. Nitrogen oxides are other kind. Typically nitrogen dioxide is the main one here. There are a few others that will spit out the top of a flare, but they usually are converted to nitrogen dioxide in the atmosphere shortly thereafter. We have two kinds of NOx that you'll find in a flare. First is thermal NOx, and that's what I mentioned, which is the nitrogen in the air and the oxygen in the air actually bonding together. Oh boy. And then the second kind is fuel-bound NOx, and that is if you have nitrogen in your fuel, which in a landfill usually means ammonia. As that ammonia gets oxidized, that will turn into NOx. We can't really do anything to lower fuel-bound NOx, but we can take steps to reduce the thermal NOx. All right, so here are our two kinds of landfill flares. We have elevated flares and closed flares. We're going to talk about elevated flares first, and then we're going to go into enclosed flares. All right, here's a whole complete landfill flare skid package with an elevated flare. So this is super old. This might be older than some people in this class. I can't believe they're still using this picture. But we've got the whole thing is put on a skid for ease of transport and installation. The flare sits on one side. We've got these landfill gas blowers right here that are applying that suction to the landfill so that we're getting a constant stream of gas. Here's our control panel. This one also has an air compressor on it to aid in valve actuation, because you need to be able to stop the flow of flammable gas if something bad is happening at your flare. You don't want to keep feeding a potential explosion. So we'll get into some of the mechanical components on Thursday, but that's what that big Ingersoll Rand tank is for. It's for your block valve. So elevated flare has a few names. Candlestick is the one I normally come across when I'm not talking about elevated flares. It's a really simple piece of equipment, probably the most simple piece of equipment you guys have been faced with this semester. It's an open pipe with a flame at the top. So that's not, we glamorize it a little bit, but essentially that's what it boils down to, is just an open pipe that you maintain fire at one end of. It's got there's a few advantages, a few disadvantages with an elevated flare. They're very cheap compared to your other options. They are a little easier to maintain because there's fewer moving parts, fewer components. There are a few problems though. You have a visible flame, so if you're by a highway, if you're by a neighborhood, people might have a problem with like walking by and seeing there's like a 20-foot long flame like shooting right over their heads. I know if you go out to Turkey Mountain, you go walking out there, there's an elevated flare right by the walking trail, and you can get close enough to that you'll actually, like, you can roast a marshmallow out there, it gets a little toasty. So that's that radiation we're talking about. You actually can't test the emissions on an elevated flare. There's no control volume, you can't put a probe anywhere, they don't control temperature, you're just kind of going on faith that this thing is doing what it's supposed to. But there are a few design criteria that the EPA has put in place where if your flare is designed with this stuff in mind, you can rest assured that it will be combusting properly and giving you the destruction efficiency and the emissions that you should. They actually established those guidelines out at our test facility. We had an elevated flare set up at our test facility, and they basically brought out this huge umbrella with a vacuum cleaner in it, and they turned on the elevated flare, turned on the vacuum, pulled all the gas, all the air coming from the top of that elevated flare into the umbrella, and checked to see what like the carbon monoxide and the NOx numbers were coming through that flue gas. And so that's how they established 40 CFR 60.18. That is your main federal guideline that regulates the design and emissions of elevated flares. AP 42 is an industrial flare regulation that will tell you what the NOx and CO numbers coming off should be. And so this is just what any elevated landfill flare in the country will mention on their air permit. They're not actually testing anything. They just take it on faith that their flare is designed in accordance with these regulations and they're achieving the NOx, CO, destruction efficiency that we tell them they are. An advantage of an elevated flare is that it has better turn down. So the max flow rate, the min flow rate, you've got a bigger gap on an elevated flare than you do with an enclosed flare. Just one of the advantages of us not actually regulating the combustion environment at all. They don't control temperature. But because we don't control it, it's a less stable flame. Windy days, rainy days, you can get blowout. So that can be a problem for your landfill guy. He has to drive out to the side at 2 a.m. because his flare blew out. It's tough being a landfill field tech. Okay, so that first regulation I mentioned, 40 CFR 60.18. That is how we size our elevated flares. It tells us how much gas we can put into a certain pipe diameter. So assume 50% methane in your landfill gas. This is the maximum flow rate we can get in each one of our elevated flares. They go from 4-inch diameter, 15 feet tall, real tiny thing, up to, as a standard, a 16-inch flare that's 45 feet tall. All of these are self-supporting. You don't need guy wires or anything. Just the anchor bolts in the base are enough to keep it upright. The elevated flare, pretty simple machine. Not a lot of components here, but we'll get into them. We have our carbon steel riser here. There's a flanged inlet right there. This is the landfill gas header going up to your flame arrestor. At the top, we have a stainless steel flare tip and a windshield to kind of protect the flame. There's thermocouples and a pilot to make sure that we actually have flame. But let's get in a little more in depth with what these components are. So riser, inlet, it's the same picture as the last slide, but here's a little closer look at a flare tip. We're going to go inside this in a couple slides, but you can see that kind of has this screen around it to keep wind and rain off the flame as much as we can. It's still tough because it's, an open pipe. But the windshield, it should protect the main flame from the wind, protect the pilot from the wind. It can be tougher to get the pilot going than the main flame in a lot of wind situations. The pilot will, have flame right there, so it makes it easier to start the main flame. The thermocouples are there to detect the flame, and the windshield kind of will direct the flame position a little bit so that we know that the thermocouples are in a good spot to get the flame. So here's a look up the stack. You can see the pilot right here. It will push some flame into the center of that pipe. And then going up, we have our main flame and our pilot thermocouples, which raise temperature in response to flame. And that's the only way we know, other than the eye test, that we have a flame. You generally don't want to rely only on the eye test because people need to go home. So the pilot up at the top of the flare, it's spark ignited, so we'll just shoot a bunch of current through, and it has an ignition rod inside, like kind of a gap that leads over to the metal side, and a spark will arc across there, and that'll be enough to ignite the natural gas or the propane that you use as your pilot fuel. To save fuel, we use that only intermittently. Once your main flame is proven, we cut off pilot flame. That's pretty standard in landfill and biogas applications, not standard in pretty much any oil and gas application. So we're kind of unique on that front. So here's looking down from the top of an elevated flare. So you can see all the different components going on at the top. These are your two main flame detecting thermocouples. Once the main flame is on, they should theoretically start raising temperature to let you know that you have a flame. Here's the pilot. It has its own thermocouple in there, and you can see it's angled to shoot flame straight into the middle. So we should be getting really good exposure and mixing of the flame with the incoming gas. And this one has a couple additional things. It has these flame retention tabs that kind of run around the rim of the riser, and that will direct the gas a little bit more, kind of shape it into a more stable flame. We'll have a slide in a little bit that shows how it shapes that. And then this right here is a continuous biogas pilot. So some sites decide they want to take just a slipstream of their landfill gas, just a little bit, like 20, 25 cubic feet per minute, and they will maintain a pilot flame at all times just to help with the flame stability and increase the turn down of their flare a little bit more. Here's the design drawing for one of these elevated flares. It lists all the connections, the bill of materials. Here's just the full stack, and you can see the top, the bottom. It's got a few different drawings, so basically our fabricator and our shop, they'll know exactly what they're supposed to do, and the installer should know what fits where once they get the flare out in the field. The design considerations that go into designing an elevated flare are going to be the exit velocity, which that goes back to that 40 CFR 60.18 law that I mentioned. The radiation level, the flame stabilization, and the turn down. But the big two are going to be your tip exit velocity and the radiation. That's what I'm going to spend the most time talking about. So exit velocity, 40 CFR 60.18. That's the law I have to talk about every single day. It tells you how fast you can shoot gas out the top of your elevated flare, and that's a function of the heating value of your gas. So if I have 50% methane, I have to maintain a certain velocity, but if I have 60%, suddenly I can have more velocity. We just want to keep the fire or the gas coming out at a speed that will keep the flame at the tip of the flare and not rising up above the windscreen so that we lose our flame. We want to maintain it right in that windshield, right at that flare tip. So we're taking the math out of it just because the equation that governs this law I've never successfully solved. Like, I've never actually come up with the right answer when I tried. So just take it on faith. If you have 2,000 SCFM at 55% methane, you're allowed to have an exit velocity of 103 feet per second. And that will tell you how much cross-sectional area you can have at your flare tip. So basically you can idealize that as the tip diameter. So if I have 2,000 SCFM, I know the cross-sectional area with these different diameters. This tells me the exit velocity that will result at a different flare diameter. The magic number is 103. I need to have a 10-inch or larger flare to be at the maximum velocity or below. Any higher than that, I can't guarantee good destruction efficiency. I can't guarantee flame stability. It's pretty important to size these things properly at the tip. So this is a sideways picture of that windscreen stabilizing the flame. We also kind of space out the windscreen so that we can kind of judge how much air is being pulled in the bottom by the flame. So that should keep it within those flammability limits. So you can see this is like infrared. This is the flame traveling out the tip of the flare. It has kind of this hang up right here where it shoots into the side of the windscreen, and it has this hot spot there, so that will hold it in place a little bit longer. You can eke out a little bit more destruction efficiency, a little more residence time before it goes above the top of the windscreen and kind of disperses into the atmosphere. And you can see in this picture, this is the spot where that flame is shooting into the windscreen. That's the hot spot where the metal looks kind of discolored because it's super hot compared to all the areas around it. Radiation levels are the other big thing with elevated flares. This is how we decide how tall they're going to be. OSHA says that if you have people continuously in the area, you need to keep it to 500 BTUs per square foot per hour. Just for a frame of reference, if you hang out outside at noon on the hottest day of summer, you're probably at about 250. So we're allowed to do double that for continuous exposure, assuming you're wearing the proper protective equipment. So hard hat, boots, gloves, all the stuff you want to be in hot weather for. That's all stuff I just told you. Let's keep moving. So this is an example of the isoplot. This shows basically the intensity of the radiation at a certain distance from your flare tip. And we will size all of our landfill flares to make sure that regardless of what's coming out the top, you're not going to be above 500 BTUs per square foot per hour at grade. So make sure you're not hurting any of the operators, because those landfill field techs, they have it hard enough already. All right, turn down, that's just your ratio of your max operating point and your minimum operating point. It's assuming constant heating value in your gas. An elevated flare will give you about 10-to-1 turn down. So if I'm at 1,000 SCFM as my top, I can drop down to about 100 SCFM before I really lose destruction efficiency and lose my flame. I think we already saw that slide. All right, so that will conclude the elevated flare portion. Any questions so far, or am I just answering every question you ever had and we don't need to talk about anything else? Let's get into enclosed flares now. So this is a little fancier, a little more expensive, a lot more expensive. This is a landfill site. I think this one's in Pennsylvania. And you can see it's got that same blower skid that the last one had, but instead of putting a tiny little candlestick on the skid, we have this behemoth flare posted up about 30 feet away from it. There's some advantages and some disadvantages with these enclosed flares. First and foremost, in the minds of the neighbors, is the hidden flame. You no longer have just a giant flame staring you in the face all the time. You could walk by one of these and not have any idea what it is. You don't know that there's a flame there. They're actually pretty quiet. Like sometimes you got to peek through the sight port to even tell it's running. There's no radiation off of them. Because there's an insulation inside the stack that keeps all that heat inside, so you don't have to worry about roasting people walking by. Because we are controlling the temperature inside the flare, you get better NOx, better CO numbers than you do with an elevated flare. But also, we don't need to take it on faith that we're getting these NOx and CO numbers, because you can actually test the emissions on one of these. So here's the sizing chart for one of these. We size those elevated flares on tip velocity. We size these ones on total heat release. So you need to have your stack can only accommodate a certain amount of heat release before it starts getting too hot and you can't control the temperature anymore, and you start kind of degrading your components, degrading the structure. So we need to know what the flow rate is. We need to know what the heating value of the gas is. And we figure out how much heat release goes in. When we have these things as small as 4 feet by 20 feet tall, all the way up to 13 feet in diameter by 60 feet tall. And we could go bigger, but it gets pretty tough to transport one of these at that point. I've heard about ones that have taken kind of like 3 months to reach their end point in the United States, because you'll drive it up to the state line. You'll call the next state and say, hey, we're bringing this large permitted load in. And they'll say, no, you're not. So at that point, the truck driver just kind of has to like leave it at the side of the road and go back to his wife and kids, and we just wait until the state says, all right, you can come in now. But I've also heard of ones that couldn't make a turn in like small town America or wherever. So just like picture some town of 2,000 people out in the middle of nowhere, has this 13-foot diameter, 60-foot tall flare stack. Turn right on Main Street. They just couldn't quite make the turn, and so it's just stuck there until they can get more guys out there, like a crane, to like turn it in place so it can keep driving down the road. Transporting these things, I'm glad I don't have to do that. So there's a lot more components on one of these enclosed flares than there is with an elevated flare. It's just a more sophisticated piece of equipment, and the components reflect that. We don't only have just the stack. There's also insulation, pilot, burner tips. There's a flame scanner. We'll get into all this stuff. This is just a brief laundry list of what we're going to talk about on these things. But there's that sample port that I talked about. If you have an enclosed flare, the state will normally once a year send out the air source testing van, where a guy gets in a man lift and goes to the top of your flare and jams a big rod through that hole in the side of the flare and just sits up there for an hour and watches the numbers rolling in on it. I was at a flare test in Phoenix, Arizona in August, and this poor guy, wearing all his flame retardant equipment, was 50 feet in the air in Phoenix, middle of summer. All he had was just like kind of one of those handheld battery-powered fans with like a mister in it. Just that poor guy. He couldn't touch the front of the man lift because it was too hot. It was burning him. Stay in school, kids. So here's a picture of an enclosed flare that most people never get to see because this is it on its side. But this is the burner manifold. This is how the gas gets in to your flare from the gas collection system at the landfill. And you can see it kind of separates into all these different burner tips. Different size flares require a different number of tips just to make sure we have a good velocity going into the flare. They don't govern these by tip velocity, but there is a range we like to keep it in so that the gas isn't going too fast and getting away from the flame, and also isn't just going too slow and the flame can propagate downward. Here's a view of the inside there. When it's upright, this is staring through one of the air dampers on the side. So Each one of these is flanged in place there, so if something breaks, you can take off one. You don't have to remove the entire manifold, which would be impossible. And these are placed below a floor, which, well, the next one's a picture of the floor. I'll show you that. So this is the floor looking down at the burner tips. That manifold is below these holes, the throat around the burner. And we make sure we get good mixing of the air and the landfill gas by all the air gets sucked in through those air dampers that you saw on the bottom of the unit, and they get pulled through the throat. And up above every one of these burner tips, we have an inverted cone, and that forces the landfill gas straight out into the throat where all the air is coming up. Now inside these burner tips, we also have a crimped metal flame arresting element. So if the flame starts propagating downward into the burner tip, that flame arrestor will soak up all the heat and drop it below the auto ignition temperature. Just a way to keep things safe, keep the flame above the flare and not below it. Another important part of any flare is going to be your pilot. The pilot on an enclosed flare we position to just kind of meet at one burner tip, but it should be enough to cross-light to all the other burner tips once you have one main flame at a burner tip. But again, it's in that throat, so we make sure we're getting good mixing of the flame and the oxygen and the fuel, everything you need to keep that combustion reaction going. So we spark that pilot with this thing right here. That's your ignition panel. It's got a 6,000 volt transformer inside it, and we send a bunch of power to it, and it generates the mini lightning strike that happens in the pilot and ignites the pilot gas. You can see right here, here's the pilot gas line. So this is hooked up to your city natural gas, and we kind of meter right here the amount of air that can get in. There's like an adjustable nozzle that you can change the width on, because we're pre-mixing the air and the pilot fuel before it gets into the flare. So we already have flame once it's coming out of the pilot. We don't need to cause two combustion reactions inside the flare. The pilot flame should arrive on its own. You can see that this is another of those air dampers. When we start turning on the flare, the air damper has these modulating louvers on it, and they are fully closed shut so that no cooling air is getting in, and we're only focusing on getting the stack up to temperature. Now we have this isn't that common, but a lot of units will have this kind of chain link mesh over it. We can't make sure, we can't make it so that the skin of these things is cool to the touch. There's fire going on inside it constantly. And in fact, we design it to stay above the boiling point of water as a way to mitigate corrosion from rainwater and condensate that may be getting in with the landfill gas. So some sites will put this screen around it so you can't touch your hand onto the flare stack and lose your fingerprints and start a life of crime. So this is the insulation that lines the entire enclosed flare stack. It's made of a ceramic fiber. We have 2 inches of it inside each flare stack, and it's held in place with these anchors. They're made out of Inconel, which is a high temperature metal alloy. Just pins and keepers every 8 inches or so all the way around the flare stack, all the way from top to bottom. I did mention that we control the temperature in these things, and the thermocouples, there will usually be 3 in the stack going up the side of the stack. The thermocouples are how we know the temperature in one of these. We actually changed the thermocouple that's registering the temperature based on the flow rate going into the flare. So you know the flame is going to get longer the more landfill gas you're sending into it. So it doesn't do you any good to be measuring the temperature when you have only 4 feet of flame. Why would you be at your 35-foot thermocouple at that point? You want to make sure you're not registering at this thermocouple until you're at max flow and you have the biggest flame possible. So just switching the thermocouple depending on flow rate lets us more accurately know what's going on in that combustion zone and make sure that the whole flare stack is in the temperature range we want it to be. And we keep it in that temperature range with these air dampers. If the temperature is getting too hot in the flare, this automated damper will open up and all the air gets sucked in by the combustion going on inside the unit. So we don't have any forced draft, it's all natural draft. The air just gets sucked in through those dampers. And they open up to full when it gets too hot. We want to keep it at about 1600 degrees. So if you're at 1700, these are open. But more commonly, when it's just turning on, they're all the way shut, so no cooling air is getting in, and all that heat is staying in the flare, and we're rising to the temperature we want to be at. A really important safety measure in any of the enclosed flares is this purge air blower. Before you start introducing flame into the flare stack, you want to make sure that you don't just have like a big pile of methane sitting in there already, because that could cause an explosion, and we don't want to do that to our landfill field techs. So we'll run this fan for about 5 minutes. It has a pressure switch above it to prove that it's working. And the air getting in through the purge blower should lift all the methane up out the top of the flare so that we have a safe condition before we spark our pilot and start the flame going on in the unit. The elevated flares, we proved flame with a thermocouple. We get a little fancier on the enclosed flares. On these ones we use a flame scanner, which is either an ultraviolet or an infrared lens that just stares at where the pilot should be. And when it notices a flame, that's how the computer says, oh, well, I've got a pilot flame now. I'll open the block valve and let the landfill gas start going. Anytime the flame scanner doesn't register a flame, it's going to trip an alarm and the flare might shut down because things aren't going the way they're supposed to at that point. Here's the view inside one of these when they're in operation. You can see that the flame kind of hangs out above those tips because it's all mixing right here, and then the flame kicks in up there. It's a yellow flame because this is this gas doesn't show up in the flare mixed. Once the flame gets going, it's looking for that oxygen, so it's going to be yellow as opposed to blue the way you get on a premix where you have all the oxygen and fuel well mixed before you start ignition. Another thing we can do with these enclosed flares is condensate injection. Landfills generate a lot of liquids. Landfill gas is all water saturated, and that can all puddle up in that gas header in the gas collection system. So what some sites do is they will pump that over to the flare and shoot it straight into the stack through one of these injectors. You have to atomize it, so you're just shooting it in as like this pressurized mist, and you don't have huge slugs of liquid going in. You just have like little droplets that easily get evaporated. But depending on the type of atomization you're doing, we need to get these up to about 300 psi gauge pressure before we shoot it in. And if one of your tips clogs, like I've seen one of these things just like drill a hole through the other side of a flare tip because it wasn't atomizing it anymore. It was just shooting in 300 psi water in a laser all the way through the flame into the other side of the flare stack. So if you are condensate injecting, maintain your equipment, don't neglect it. We do need a set amount of heat to allow condensate injection. You want at least 10 million BTUs an hour of heat release before you start shooting in 1 gallon per minute. And I would not recommend ever going above 1 gallon per minute because that's just more tips to check after, more potential for clogging, and lasers drilling holes in the opposite side of your flare tip, or your flare stack, sorry. This is what that injector looks like inside the flare. You can see it poking in through the insulation. This flare is not on currently. Other things that we can do on these flare stacks to assist with source testing and maintenance, you have a ladder that will run the length of the flare. See, this line right here is your thermocouples detecting the stack temperature. So you don't need to get a man lift out anymore. You can just climb the ladder, swap out the thermocouple, and then go back down. or you can go up on this service platform and source test from up there. So another reason you don't need a man lift. This one's more of like a sales pitch slide. I should have deleted this one, but for ease of maintenance, we like to hinge one of those air dampers so you can get inside. You don't need to fully remove it. Here's the design drawing on an enclosed flare. So you can see like this stack is such and such high, so wide. It's got 6 burner tips inside it, and that larger circle around each tip is the throat, where all the air is coming up from the dampers getting above the floor. Here's a manifold drawing, so you can see the manifold coming in here, and then you can see the burner tips coming up from that manifold. Here's the damper frame. This one should have 2 dampers on it, and this will tell you basically you need this many dampers at this size, or where the purge air blower sits. Basically, same as that last design drawing, this will tell the people in the field what goes where, tell fabricators in the shop how it needs to look. So when we design an enclosed flare, it's pretty different than sizing an elevated flare. We're not worried about radiation anymore. We're not as worried about flow rate. It really comes down to heat release with an enclosed flare. Heat release is a function of flow rate and the heating value of your gas. We size based on millions of BTUs an hour. So we have our flow rate, the heating value, and then multiply it by 60 to get it out to an hour. And that'll tell us how big the stack needs to be so that we get like the best turn down possible and also aren't overheating the stack and reduce like hurting the structural integrity of it. Also make sure we don't have flames coming out the top of the enclosed flare. I've seen it, it's not good. So the operating temperature, we normally want it between 1400 and 1800. Around 1800 you start seeing NOx really go up. But when you're down at 1400 you can have some serious CO2 or carbon monoxide issues. So 1600 is normally around where we are, and all the temperature is maintained basically solely by the amount of cooling air we're letting into the flare. So we know how much air we need to let in for every million BTUs in order to achieve a certain operating temperature. To keep it around 1600, where we usually want to be, you're going to need 505 cubic feet of air every minute going in for every million BTUs of heat release you have going on. And using my fanciest graphics, that's just shows where the air is getting in. Both these dampers modulate to open up or close depending on where the temperature in the flare stack is. Flame length is another design consideration. This is going to be a function of the velocity that the gas is going in, the heating value of your gas, and the operating temperature. And these kind of react in ways that seem a little counterintuitive. Like as the velocity of the gas going in increases, you would think, you just kind of intuit that the flame length would increase, but it actually decreases because all of these are a result of the fuel and the air finding each other in the right amounts. The faster the gas is going in, the quicker it'll mix with that air and the quicker the flame will extinguish. If you aren't, it's just turbulent versus laminar flow really. Like if you're shooting the gas in slowly, it's not mixing, it's not generating any turbulence. So that flame is going to last longer, traveling up the stack looking for more and more air until it has all that it needs. As the heating value of the gas increases, the flame length increases. And that's just the same kind of deal. If you have more fuel going in, it needs more air. So that flame is going to last longer before it's extinguished. And the temperature increasing causing the flame length to increase. This is because, what did I tell you guys about the cooling air? That's the only way that we regulate temperature. So if you are at a lower temperature, there's more air there. So if the temperature is hot, there's less air, the flame is going to last longer until it finds all the oxygen it needs to terminate. Here's a diagram that just kind of shows how these different things interact to create flame length. So the heat release, the operating temperature, the heating value of the gas, they'll all interact to make a longer flame as the methane content of the gas increases, as the temperature increases. So by the time we get down here to 65% methane with 1800 degrees, like suddenly we're higher than a 40-foot flame. Retention time is the last design thing that we bring into the enclosed flares. As a regulatory standard, pretty much every enclosed flare needs at least 0.7 seconds of residence time, and that's just how long it takes to get from the burner tip up to the sample port. It's not the top of the flare, it's actually the sample port, because that's where the local DEP is going to be sticking the air source testing rod. So you need to have your destruction efficiency achieved at that point in time. And then turn down, same as an elevated flare. That's just your ratio of your max operating point to your minimum operating point. And that's not dependent on flow. That's entirely dependent on heat release. If you have really variable gas quality, like the flow rate range you can get away with might be really different from the 8 to 1 that we assume you can do on an enclosed flare. It's kind of limited because you need to be able to more tightly control the amount of air getting in, and there's just a certain amount that's going to get in through like cracks in the air damper, through that purge blower. Air can get sucked into the purge blower. Like if you think about like standing by a front door on a cold day, you can feel that draft down by your feet. That's what's limiting us here, is just air getting in where we don't want it to. So we generally say you need to have about 2.5 to 3 million BTUs an hour in an enclosed flare to keep that temperature where you need it to be. But there are ways that we can improve the turn down, and they're all about just keeping air out. You can totally close the air damper. You could completely blind it off, seal it off with a piece of sheet metal. Or you can get another thermocouple lower down closer to the flame, so that you can get away with a smaller flame, less flow rate, less air getting in. All right, so let's do a quick exercise here to design for the retention time. This is what we need. This is how we'll size it. Let's just say we have 2,000 SCFM at 55% methane, and we want to be operating at 1,600 degrees. This would be a really common, really standard landfill application. So we design we can calculate our heat release by the flow rate, by the heating value of the gas, 910 for the methane times the percent that is methane, get it out to an hour. So we know we have 60 million BTUs an hour of heat release going on in this enclosed flare. Just because we have decades of experience doing this, we know that we should probably be around a 9-foot diameter, 40-foot flare with 7 burner tips at that size. And I'll show you kind of how we get there. So I said a 9-foot diameter stack, but it has thickness. It's going to have kind of a 3/8 inch thick steel shell, as well as the 2 inches of insulation. So the effective diameter is only 8.63 feet, and then we only have 30 feet of vertical volume, because that floor that I showed you is about 5 feet, and then the sample ports are going to be 5 feet down from the top of the stack. So remember, I talked about how much air you need to achieve a certain temperature. So we need 505 standard cubic feet of air every minute for every million BTUs of heat release, and we know we have 60 million BTUs of heat release in this unit. So that is how much air we need going in every minute, 30,300 cubic feet. And so our exhaust gas flow coming out the top will be the 2,000 cubic feet of your landfill gas, in addition to all the air you need. So you're up to 32,300 cubic feet coming out every minute of the top of your stack. So that at 1,600 degrees, you have to correct for the volume, because a standard cubic foot has an assumed temperature, and we're a lot hotter than that. So we're actually going to be having exhaust gas coming out the top at 2,132 actual cubic feet every second. We know our stack volume, and then it's just a simple matter of division of to give you a residence time of 0.83 seconds, just above the 0.7 seconds we want. We're close to wrapping up here, but this one's kind of a preview of Thursday a little bit. There are some specialty flares where if just the normal landfill gas flares aren't cutting it, we can provide for other sites. The Zebrid is a kind of a hybrid flare that if you have a beneficial use plant at your landfill, like you're taking all that landfill gas, you're converting it into renewable natural gas, like you're stripping out all the carbon dioxide, you're stripping out all the water, you're pressurizing it, you're selling it to the pipeline. You're going to have some low BTU tail gas left over, usually about 5 to 10% methane, and the balance of that will be carbon dioxide. You can't free vent that because it's going to stink like landfill gas, and the methane is going to have a very potent greenhouse gas effect. So this is a unit where that non-combustible tail gas will shoot in through this external manifold right here, and then we have a fuel gas coming in from the bottom. And this has a few modifications to minimize the amount of fuel gas going in, which we'll talk about on Thursday. Also, we have this off-gas flare, which is used to burn siloxane regen streams. Siloxanes are this ingredient in landfill gas that's usually a result of cosmetics and some food products that can gum up engines and other like small piping networks because they just form this nasty film or this crust. And so there's temperature swing absorption systems put in place upstream of any renewable natural gas or turbine set up at a landfill, where they'll just stick all these siloxanes on a granular media in these tanks, and eventually you need to regenerate this media. So they'll blast air through it and then send it to a flare to burn off all that siloxane in a place where it's not going to gum up any equipment. So when you look at one of these, you can normally see like a white film around the top because the siloxane's crusting up at the top of it, but your engines are still working. The last type of specialty equipment that we're going to talk about on Thursday is the Zool, where my Ghostbusters fans at. It's our ultra-low emissions flare. It's a premix flare. So you see this air blower here. It shoots a set amount of air into this mixing chamber where the landfill gas meets it. So suddenly we now have a premix flare. We're not relying on the natural draft coming in through those air dampers. And as a result of this, we can get by with lower CO and lower NOx because there's better mixing, so we don't have incomplete combustion. There are portions of California where you are now mandated to have an ultra-low emissions flare. Also, Canada is pretty into the ultra-low emissions flares. But we'll get into why this works a little bit more on Thursday. It's not just landfills that we deal with, though. There's also digesters. This is a wastewater treatment plant in Phoenix. I've been there. I've had better vacations. But this is basically the way a traditional wastewater treatment plant works is all the wastewater will sit in these large tanks back there where bacterial action will degrade the organics, and as a result you end up with a lot of biogas. And this is normally a lot richer gas than you'll get in a landfill setup. Normally 60 to 65% is common, but I've seen digesters up to 80% methane. And there's some other design considerations that have to go into that. You're going to have a hotter flame, so you're going to have higher NOx, and you're going to have a longer flame, so you generally will have a taller flare stack. But there's a lot of pressure built up in these things, so there's normally a lot of design considerations, and they're highly spec'd out, and they can be kind of a pain. But you don't need to have that blower skid because you're not pulling on anything anymore. You just open a valve and the digester gas will flow right to you. So this is that chart again, showing a flame length and 65% methane where we're going to be in a digester. We're safely over that 40-foot line, so our standard size flare isn't going to work anymore. We need to add on an additional 10 feet generally. So this is our same sizing chart, but assuming 65% methane, and we don't start at a 4x20 anymore. Now we start at a 4x30, and we can actually take these out to 13x70, but we would prefer to just stick with that same 13x60. But we can't get up to 6,000 cubic feet of gas anymore. Now we're topped out at about 4,200. So just closing out, we have a few scenic photos of landfill installations. This is an enclosed flare and blower skid. I think this is another one in Pennsylvania. There's a lot of landfills in Pennsylvania. It's a two-blower skid. There's a compressed air tank for your block valve. There's a control panel on it. This is that same elevated flare that we showed at the start. It's got that compressor, control panel, two blowers. This is a little fancier. This landfill is still growing, so they sized everything for a future expansion. So this is a spot on their skid for a third blower. They only needed two at this time, but this will allow them, with a pretty minor retrofit in the future, to add on a third blower and pull extra gas out of their hill. The flare should be sized for that future expansion. You can also you don't have to bolt the elevated flare directly into the ground. You skid mount it, and to help get it out to the site, we put a hinge on it so it will fold down and kind of run the length of the blower skid in transit. And then it's just a matter of having a guy with a wire or a pneumatic pump or something like that raise it in place. So it helps a lot with installation. And with some of the bigger ones that we hinge in place, we'll put a service platform on there too. So you can climb up and swap out your pilot, swap out your thermocouples without having to climb 40 feet in the air. This one also is sized for a future third blower. That's a pretty fancy system. And then this is just an enormous landfill. I think this one's in South America. They're taking two 13-foot flares because they're just generating so much landfill gas. You can see it's got a common skid, and then the header splits out here, and they'll have control valves that will regulate the flow so that they're evenly spread between the two flares and we're not overfiring anything. We made it. That's the end of part one. It's the longer part of the two, so we might cut it a little shorter on Thursday. But does anyone have any questions?